Hello and welcome to another session of the Digital WE Days. My name is Silas Ton and I will moderate this webinar today. Our topic of today is designing system-level power solutions. Our speaker today is Allard van der Horst from Analog Devices. He will hold the presentation. And his colleague, Glenn Amparo, will answer your questions live after the recording. So yeah, efficient power system requires smart architecture and integration. But how do you go from concept to real-world application? Let's learn from the expert. Stage is yours.
Hello everyone. Welcome to this webinar on designing system-level power solutions. Did you know that the average US household has over 50 power supplies, power bricks, chargers, etc.? And it's expected that more techie people have more than 100. And this does not even include power solutions inside the box. My name is Allard van Horst, and I lead a team of power system architects at Analog Devices. A team solving power challenges at the system level every day. And in this webinar, I'll be sharing some of our experiences in doing this. In the next 30 minutes, I plan to give you some insight into some of the best practices, enabling us to find the best power solutions for a wide range of applications. In the end, every application needs power, so finding optimal power solutions is critical. As you may know, Analog Devices is a combination of 3 companies and all the expertise that came with that in power. Did you know that our combined portfolio has over 20,000 power products? Analog Devices, Linear Tech, and Maxim uniquely complement each other. Linear Tech excelled in high power density, unique packaging, low noise performance, and design and simulation tools. Maxim Integrated came with real leadership in low power, nano power, integrated solutions, and power technologies. Analog Devices excels at precision power and has huge signal chain and system expertise that comes with all the signal chain and systems products that they make. So this combined strength enables us to be technology leaders in power. And this is demonstrated by over 2,000 patents in this area. We have a real wide range of power technologies, enabling us to address a wide range of power problems. So let me give you an idea of what some of these technologies are. As I said, we have a huge portfolio, but it doesn't just consist of a full range of boost, bugs, LDOs, etc., but covers a wide range of key technologies. Now, these different technologies have their own strengths and will enable addressing a huge range of applications with optimal solutions. So what am I talking about? Let me give you some examples, okay? So first of all, silent switcher, for example. Silent switcher technology provides ultra-low noise switching regulators with excellent transient response. The hot loop, which often is the source of noise, is divided into 2 smaller loops and placed around the IC. And this successfully contains the magnetic field and prevents EMI propagation and reduces noise. And then there's micromodule technology, introduced by Linear Tech about 20 years ago. This now offers unprecedented levels of power density, critical in many applications, as I'm sure you know. Also, these micromodules are complete off-the-shelf solutions, so it provides guaranteed performance and minimum design in time. And the third technology I want to mention is DPSM, Digital Power System Management. So this provides control and observability, which is critical in many cases, specifically with power systems becoming more and more complex. Not only does DPSM help to control the sequencing, it provides a lot of insight and fault management. And that plays a really big role in applications needing, for example, functional safety. And this is an area that is receiving increased attention and requires us to find power solutions, right? Here's some more detail on the silent switcher regulator family. As with every family, there are multiple branches with, for example, the low IQ silent switcher branch, the ultra low noise silent switcher 3 parts, and silent switchers with telemetry. This is a very versatile technology, which really helps with optimal system level power design. In many cases, for example, it's possible to eliminate the LDOs, as the noise of the switcher is so low. This, in itself, improves efficiency and reduces footprint, while ensuring excellent performance still. Multiple silent switchers can be put in parallel, enabling support for much higher currents. As you can see from these high-level specs, these parts are very useful in many applications and an excellent tool in our toolbox. This picture of a micromodule shows the amount of technology that's integrated. By having everything integrated, the performance can be guaranteed and the size can be reduced. In other micromodules, the inductor can be placed on top of the chip, which again helps to reduce the size further. There are even micromodules with built-in EMI shielding, enabling placement close to sensitive nodes without causing any impairments. Again, you can see how micromodule technology can be extremely useful addressing certain system-level power challenges. So, these are just a couple of the advanced power technologies we have to our disposal. Understanding their properties and benefits, as well as the limitations, is important in understanding what to use in a particular solution. So then, let's talk about the component selection. A topic that might seem straightforward at first, but is actually deeply nuanced when designing a successful system. As I said, we're fortunate to have a vast portfolio of products at our disposal. But with that comes the challenge, right? How do we choose the right one? Each technology has its own strengths, and selecting the right component requires more than just comparing datasheets. And this is one of my key messages. This is where a holistic, system-level approach becomes essential. We need to start by understanding the system requirements. And that's not really just what the customer asks for, but what is truly needed, what's good enough for the application. And that leads to a better power systems design. So to break that down, right, there's all these aspects. There's performance. Of course, we look at efficiency, noise and ripple, transient response and EMI. These are the fundamental specs that we all get, but they're just the beginning. And there's cost, right? It's not just about the cost or the price of a component. We need to consider the whole BOM cost, bill of materials, and development cost. All of that provides a more complete picture. Size, also critical often. And just like with cost, it's not just the component size, it's the BOM size, right? The PCB place and route constraints that play a huge role. In fact, sometimes using several smaller components gives us more flexibility than a single multi-channel part, even if that part is technically smaller. And then there's the signal chain impact. And this is often the hardest to quantify, but arguably the most critical. We need to consider both noise sensitivity and generation, as well as transient requirements. All of this points to one key takeaway. Power cannot be an afterthought. Starting the power discussion early and aligning it with system level requirements is crucial to achieving the best solution. So let us move from a product-centric mindset to a system-centric one, because that is where the real design success begins. Selecting components is just the starting point. Right? True system-level power design demands integration with the signal chain. In signal chain applications, whether it's communications, data conversion, or high-speed interfaces, power supply noise directly impacts signal integrity. Yet, this impact is often under-characterized, and especially during the early design phases. So, addressing this, we see typically two integration approaches. The first is the best effort approach, right? Where you have a generic power solution applied with limited system insight. It may meet basic specs, but it often underperforms in real-world conditions. And it's also not the most optimal solution. And then there's co-design, a tailored power architecture developed with detailed signal chain knowledge. This enables optimized noise performance, transient response, and EMI behavior, but also optimized cost and size. So this is where adopting signal chain and power solutions from a single vendor can offer real benefits. Different teams on the same company can collaborate in an open way and highly technical level to find the optimal solution for the application. So this is exactly what my team in Analog Devices does every day. Working with signal chain product experts, co-creating, finding the optimal solution for power. Not only in performance, but also in cost and size. Effective integration means aligning power design with signal chain requirements from the outset, not as an afterthought. This is essential for achieving robust, high-performance systems, reducing risks, and improving time to market. Optimizing co-design requires the right tools. Analog Devices offers a complete suite for power solution design, and it's free. The tools in this suite are LT Power Planner, LT Power CAD, and LT Spice. To start, LT Power Planner helps you design and optimize system-level block diagrams, estimate efficiency, and arrange components. We use this tool to start the design work, figure out the power tree, identify the overall high-level efficiency. And this information then can be shared with the customer for feedback. LT Power CAD guides you through regulator design, suggests parts, and shows key performance metrics. You can even export designs to LT Spice for time domain simulation. So this tool provides us with a detailed design of each of the segments of the power solution. And that includes detailed information like body plot, ripple, and transient performance. All of that can be identified at the block level. And then definitely LT Spice, which delivers fast schematic capture, waveform viewing, and simulation with a huge model library. Importing the power solution blocks enables the co-simulation to design signal chain components and determine overall performance. Together, these tools make power design easier, faster, and more accurate, all at no cost. Then the next step is prototyping, right? We have the design, we'll start to build it. Early prototyping is important, and especially for power. Power isn't just supporting a function, it directly affects the system performance, especially in sensitive signal chain applications. So to get it right, observability is the key. You need to be able to measure and validate your power solution during the development. This is where tools like LT Power Analyzer come in. Paired with the M2K Advanced Active Learning module, it gives you a powerful, low-cost setup to monitor ripple, transients, and dynamic behavior, all critical for ensuring your design meets real-world demands. And remember, you're not alone. Your Analog Devices field application engineer is here to support you. The deep product knowledge and the system-level expertise to help you review your design and make the right choices. So, start early, measure thoroughly, and collaborate. That's how you build robust, reliable systems from prototype to production. So here it is. Show you the LT Power Analyzer, which is a versatile power analysis tool that brings lab-grade performance to your bench in a compact and affordable package. As I said, it measures critical parameters like body plots, transient response, ripple, impedance, and it covers frequencies from 100 Hz to 10 MHz, and even slew rates up to 500 amps per microsecond. So this design, powered by Analog Devices technology, is designed for real-world signal insights and fast validation. Scan the QR code and learn more and get started. Optimizing co-design requires the use of the right tools. Analog Devices offers a complete suite of power solutions designs, and it's free. There's LT Power Planner, which helps you design and optimize system-level block diagrams, estimate efficiency, and arrange components. That's where we often start. The next step is LT PowerCAD, which can guide you through regulator design, suggest parts, shows key performance metrics, and you can even export the design then into LT Spice for time domain simulation. LT Spice, of course, we all know it, offers fast schematic capture, waveform viewing, and simulation with a huge model library. And this is where we can co-simulate power and signal chain. And together these tools make power design easier, faster, and more accurate. And it's absolutely free. There's no cost. So one example I would like to give is the optimization power solution for a high-speed ADC. The initial design is based on best practices, isolating the different power domains with LDOs and farad beads. As you can see, this leads to a large design which was not very power efficient. To enable particular real-world applications, the power solution needed to be much smaller and more efficient. By using detailed information about the different power domains and the sensitivities, we're able to reduce the component count and improve the efficiency. Then we further used micromodules to enable shrinking of the total size even further. So this led to a 70% area reduction and 30% efficiency improvement. And in the end, it was a successful product by the customer. So, if there's anything I hope to have conveyed in this short presentation, it's the following 4 messages. 1. Start early. Think about power from the start of your project. That enables you to get an overall better solution with higher performance and lower cost. 2. Thoroughly understand the system. The better the understanding, the more optimal power solution will be. 3. Tools. There are a lot of tools available to optimize your solution as early as possible. That includes simulation. And finally, when you prototype, add observability. Make sure you can see the power so you can find any issues quickly and optimize. Together, these 4 concepts form a robust framework for success in designing system-level power solutions. And don't forget, if you need any help with power solutions, please engage with your analog devices FAE early on. And let us collaborate to find optimal solutions. Thank you for your time, and please let me know if you have any questions.
Yeah, thank you, Allard, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, I will share the handout from the presentation, and then we can start. So now everybody can download it. Okay, yeah. Hello, Glenn. Can you hear me?
Yes, I can hear you.
Perfect. Perfect. Are you ready for the questions?
Yes, I hope so.
Perfect. Okay. Then I think.
So how do you?
Yeah. Sorry.
So how would you like to proceed with the questions?
Yeah. I would start with the first question. This one. What is the typical switching frequency in module products?
Okay. Typical switching frequency of our silent switcher module regulators typically ranges from about 200 kilohertz to 3 megahertz. There are some newer versions that would go up to about 5 megahertz of switching frequencies. So yeah, those are the typical switching frequencies of our micromodules and typically on the silent switcher products.
Okay, thank you. Then next questions. You talked a lot because talked about the power design system approach. Are there some relevant pillars to be focused on when starting a new design or to optimize an old one? Can you have a bit higher focus on the system approach?
So thank you for that question. So you would like to understand on how we are approaching a system level design or coming up with a power solution system level design. First of all, we need to, as Allard had mentioned, we need to understand what the system is really doing. So there are typically 3 pillars that we are using for designing a power supply, and that depends on what the requirements are. So when you ask the customer, what are you designing for? Are you designing for a specific performance? Are you designing for size, or are you designing optimized for cost? Well, one thing that I do get from our customers is they typically ask, "Can I get everything?" The answer to that is not really. Usually, you would like to focus on a couple of things where it's either you are looking for a certain performance, certain efficiency, ripple that's needed by the whole system. So, for example, you're designing something like on a precision signal chain. Things like ripple and noise is going to be very important to your design. So that could be your primary focus in terms of performance. Now, the next question is there any size restrictions? Is it going to be limited in the X and Y, or is there also a Z dimension that you need to consider? And now the very last thing that is always a drive by the customers is, can we have it as cheap as possible? So that is something that is going to be something that's as a consideration and a trade-off, where if you would like something that is a high performance, typically it would come with the trade-off of cost. But at the same time, we could also consider, for example, coming in from a micro modular and integrated solution to a discrete solution with a trade-off of size. So that could be certain pieces that you could consider when trying to design a power system or a power solution for the system. What you need to keep in mind first is what is the requirements for the bigger system. It comes with the understanding of a full understanding of the problem you're trying to solve first, and then designing in and plugging in the right parts that would solve um, and meet those design requirements from your customer. I hope that kind of clarify it.
Yeah, thank you. Then next question. I see there was an announcement on IDA Power Studio. What is this?
Okay, so that is a good question, and unfortunately, we just did not have time to put it into the presentation. But ADI Power Studio was indeed announced just very recently, and ADI Power Studio um, is something that provides engineers a comprehensive set of tools that streamline the design from conception to measurement and evaluation. These are a set of dedicated tools for exploring the architectures, selecting and optimizing the components, and simulating real world performance. And of course, you can also generate bombs and the reports. So by aligning all of the tools and the features of each stage in the design process, Power Studio is able to help engineers simplify the complexity, validate the designs early, and optimize the architectures efficiently. So this is a set of tools that's really combined to really help the engineer solve real world problems.
Thank you. Then next question. What EMI filtering is present in the modules?
Um, okay. This is something that I do not have the answer to. Is it possible that we can take that question offline and get back to you with an answer on the email? I am afraid that would be very product specific. I can go back and ask the applications engineers and get back to you on the answer for that.
Yep, of course, yeah. Okay, then Steve, good question, but yeah, Allard or
Sorry.
Glenn will answer it via email in the next days. Yeah, but good question. Okay, then next question. What kind of molding do you use for the module products? What is the thermal conductivity?
Again, this is I apologize once again. This is something that's product specific that I will have to defer to the applications engineers for the parts to get these answers.
Okay. Next question. Are there modules with silent switcher technology?
Okay. Yes, there is. There are micro modules that have the silent switcher technology. They include all of the features of the silent switcher technology. Plus, these micro modules have higher efficiency with the smaller board area. They can have multiple outputs, integrated EMI shielding within that package. These micro modules also have ultra high PSRR. Additional features would also include, because they're co-packaged, they're molded into single package. They typically would have better thermal performance because of it's a system in package. And overall, this is a smaller solution and therefore saving you space on your PCB. So yes, we do have silent switchers and micro module package.
Okay, thank you. Then I would say one last question. What sort of telemetry data is possible with the silent switcher parts?
Okay, telemetry. So the telemetry data that is available with the silent switcher parts is usually the output voltage, the output current, input voltage. You are also able to extract the temperature of the die. You can also get different types of faults, system faults from the telemetry, and all of this is going to be available via the PM bus or the I2C interface. Trying to see if I forget any more telemetry data. But yeah, those would be the common ones that we can take out of the silent switcher parts.
Okay, thank you, Glenn. Then I would say we are finished with the session. Yeah, when you have any questions, write into the chat, and then Glenn or Allard will answer it via email in the next days. So yeah, thank you, Glenn, for your time. Yeah, thank you for your attention. I hope you enjoyed it. Now I would share the link to our homepage of the Digital WE Days. So check it out. Please register now. And yeah, we had a lot of other sessions planned during this week. Yeah, hopefully we see us on our next session. Thank you. Have a nice day and goodbye.
Thank you. Bye. Good day.